Today I'm pleased to introduce Alex Gunderson, who's our speaker. He's going to be talking about physiological ecology, climate change, and the Anolis adaptive radiation. Alex is a postdoc with Jonathan Stillman. He received his bachelor's at Minnesota State University. He did a master's at the College of William and Mary on interactions between feather-degrading bacteria and feather coloration. That sounds really cool. And then did his PhD at Duke University, and the topic was physiological ecology and vulnerability to climate warming in Anolis with Manuel Leal. And he's been at the Tiburon Center, but has just recently moved into this building. And do you know your office number?
5041.
5041. So if you want to speak with Alex more, that's where you can find him. And the fun fact I have is that you used to be a freshwater fishing guide in northern Minnesota. So if you have questions about freshwater fishing, he's your man. Alex, thanks for coming and giving a talk.
Okay. All right, well, thanks everyone for coming. And as Michael said, I've just moved over here, so I look forward to getting to know many of you in the coming weeks and months. So I consider myself a physiological ecologist that specializes in thermal biology. And within that realm, I've been working primarily with Anolis lizards for my dissertation, and now with Jonathan, I'm moving on to sort of different types of analyses, and I'll mostly focus on my dissertation work with Anolis, and then you'll get a little bit about what I'm working on with Jonathan towards the end. And within this realm of physiological ecology and thermal biology, I'm really interested in how thermal environments shape physiological, shape physiological and behavioral traits, and then what the ecological consequences of the behavioral and physiological traits that we see are. And today I'm going to be focusing mostly on the sort of evolution and physiology axis here. For those of you who saw my HERP group talk about a month ago, I focused a lot more on this behavioral aspect, but that's not going to show up too much in this talk today. There'll be a little bit of behavior, but not much. So there are three general parts of my talk today. The first is going to be looking at the evolution of thermal physiology within Anolis, and there are two subcategories within this. One is going to be looking at physiological divergence as a driver of the Anolis adaptive radiation, and the second is evidence of contemporary evolution of thermal physiology within Anolis. Then we're going to switch gears a little bit and talk about climate change, an analysis I did of geographic patterns of vulnerability to warming within an anole. And finally, we'll end with some work I'm doing in Jonathan's lab, looking broadly. Why is that not there? Well, I'll tell you what it is. The third one is going to be looking at drivers of the evolution of plasticity in thermal physiology across active therms. And for those of you who were at the HERP group talk, I'll just tell you, you should stay awake for this part. You can fall asleep here and here, because you've already seen that. And the third part, which somehow disappeared, you should wake up for it. So, we'll start at the beginning. When most people think about the Anolis adaptive radiation, what they think about is ecomorphs and morphological evolution, specialization to occur in different structural niche, along different places along the structural niche axis, which is essentially different perch types within forests. This has been studied a lot, of course, by Jonathan Losos's lab and colleagues, and we know a lot about this aspect of the radiation. But most adaptive radiations are not one-trick ponies, right? There's usually multiple axes of ecological divergence, and anoles are no exception to that rule. We've known for a long time that the climatic niche axis is an important ecological axis of divergence within this radiation. So what you're looking at here are body temperature distributions of anoles from Cuba, and we can see that there are some species that occur in relatively warm niches, others that occur in relatively cool niches. And what's interesting about this climatic niche axis relative to the ecomorph story is that we know a lot about the phenotypic changes that have accompanied this divergence, but we actually know very little about the physiological consequences of this climatic niche divergence within this radiation. And that's what I'm going to focus on in this part of my talk. And in doing so, I'm going to address four general questions. First, what are the physiological traits involved in thermal adaptation within anoles? Second, what are the performance consequences of this physiological divergence? Can we find evidence that the divergence that we see is actually adaptive in the context of the thermal environment that these anoles experience in the field? Third, does physiological divergence promote species co-occurrence? So the ecomorph story is interesting not just because it leads to these different morphological types, but because what it allows is partitioning of the habitat and the maintenance of these very diverse anole communities. I'm going to assess whether physiological divergence can have a similar effect. And finally, how common is climatic niche divergence within the Anolis radiation? And for this part of the talk, I'm going to look at patterns of divergence in climatic niche relative to patterns of divergence in ecomorphology. I'm going to be focusing primarily on anoles from Puerto Rico. I also have data for Jamaican anoles, and those will come up a little bit later, but for now we'll focus on Puerto Rico. And there are 10 species on Puerto Rico, 8 of which fall into this cristatellus species group. And what's interesting about these 8 species is that they form 4 sister species pairs. And conveniently, we know from natural history data on these species that within each one of these sister species pairs, each species occupies a different climatic niche. So we have a relatively cool niche species and a relatively warm niche species. So we have a really nice natural experiment here of 4 replicated divergence events in climatic niche with which to assess adaptation in thermal physiology. So this leads to question number 1. What are the physiological traits involved in adaptation to different thermal niches? So what you're looking at here is what we call a thermal performance curve. And that describes how physiological rates change with body temperature. And there are a couple of features of this thermal performance curve that I'm going to focus on. First, the critical thermal maximum. This is essentially just the upper thermal limit, upper thermal tolerance limit of a species. And the next is what we call the optimal temperature, or the temperature at which physiological rates or physiological capacities are maximized. So I measured these traits on anoles across Puerto Rico and Jamaica. I did this all in the field in Puerto Rico and Jamaica. So here's my obligatory pictures of the Caribbean. So for this optimal temperature, what I measured was sprint speed, a very common metric to use in physiology with reptiles. I set up this ramp. I ran them on this ramp. I filmed them at high speed. What you can't see off camera are a couple of portable incubators that I used to change their body temperatures. So I ran individuals at a number of different temperatures and then fit a curve to those and estimated an optimal temperature for each individual. For critical thermal maximum, what I essentially did was stick them under a lamp and heat them up, and I flipped them over at regular intervals, and you wait for the temperature at which you flip them over and they can't flip themselves back over, right? They can't right themselves. Another very common metric of thermal tolerance in ectotherms. And what you might note here is that there's this wire coming out of this anoles behind. What that is a thermocouple probe that's affixed inside the cloaca. What that allowed me to do is measure their body temperatures in sort of real time. So I was able to do a couple things under this design. I could monitor the rates of temperature change so that I knew that I could keep a constant rate across individuals and species that might be of different sizes and have different thermal inertias. And I could also flip these guys over at the same thermal time points, right? So I have a lot of control with this design. So let's get right to the data. And I'll start with thermal tolerance. So let me give you a moment to sort of take a moment to orient you to this figure. What you see here on the x-axis is the critical thermal maximum, or thermal tolerance. We have species on the y-axis, and each one of these columns is a different sister species pair, with the cool habitat species in blue and the warm habitat species in red. What we see is that in 3 of the 4 cases, the warm niche species has a significantly higher thermal tolerance than the cool niche species. Okay? So what about optimal temperature? Similar figure, except this time on the x-axis, we now have that optimal temperature metric. What we see here is that in 2 of the 4 sister species pairs, the warm niche species has a significantly higher optimal temperature than the cool niche species. Now, I should point out here, there's not a lot of phenotypic variation for these 2 warm niche species. The reason for that is the highest temperature that I measured sprinting was 35, and I did that based on preliminary analyses where it looked like all the species should be coming down at that point. But these 2 species, their performance curves were still on the way up, right? So their optimal temperatures are actually further, they're somewhere up here, okay? but nonetheless we see significant divergence in this optimal temperature. So what we have is in all 4 sister species pairs, we have evidence of divergence in thermal physiology. In some cases it's in optimal temperature, in some cases it's in thermal tolerance, and in some cases So of course, observing repeated evolution is evidence of adaptation, but it'd be nice to know if there's evidence that the traits that I'm measuring here actually have some adaptive significance, or if they're just correlated with other traits that are actually adaptive. This leads to my second question. What are the performance consequences of this physiological divergence? So along with these physiology measurements, I also did detailed measurements of thermal habitats within Puerto Rico. And that's the data I'm going to show you here. So I did this in both relatively cool shaded habitats and warmer open habitats. And what you're looking at here are what we call operative temperature distributions. Now an operative temperature is a sort of more nuanced metric of a thermal environment than simply air temperature, and it integrates all the different factors that can influence body temperature, including things like wind speed and radiation and conduction with the substrate. And to measure operative temperatures, I use physical models. So I have these hollow copper lizard models that are in the shape of a lizard, and they have a thermocouple probe affixed inside. And these models have the nice quality that wherever you put them, they will equilibrate to the same temperature that a lizard would in that spot. Okay? So what you can then do is put these randomly throughout habitats and get a distribution of the thermal environment as the organism would actually experience it. With these data, what I did was ask, what's the probability that a species would overheat within these thermal environments given their thermal tolerance? Okay? Now I'll just say straight away that there was no evidence that any of these species would be at threat of overheating within these cooler shaded environments. But in the open habitat, where all of these warm niche species occur, it's a different story. So what you're looking at here, on the y-axis we have probability of exceeding the CT max, or probability of overheating. Each one of these graphs is one sister species pair. There are 3 because remember there are only 3 pairs in which I observed significant divergence in thermal tolerance. Again, the cool habitat species in blue, warm habitat species in red. And in all 3 cases, what we see is that the warm niche species has a significantly lower chance of overheating within the warm habitat relative to the cool niche species. Okay? So here's evidence that this divergence and this particular trait has some adaptive significance within the environments that these guys experience in the field. Question 3. Does this physiological divergence promote species co-occurrence? So when you look at anole communities in the field, you often see multiple species representing multiple ecomorphs. But it's also true that you often see multiple members of the same ecomorph co-occurring. So for instance, you might have a couple of trunk crown anoles or a couple of grass bush anoles. In this case, it's clearly not ecomorphological divergence that's allowing them to co-occur, right? Something else must be going on. Maybe it's thermal physiology. So what I did was compare the thermal physiologies of all cases across Puerto Rico and Jamaica in which morphologically similar species co-occur, and asked if there was physiological divergence between those 2 species, or physiological differences. So, for example, on Puerto Rico, Anolis stratulus and Anolis evermanni co-occur. They're both they both occupy the same location along the structural niche axis. They're both trunk crown anoles. And what we see is that they differ in both critical thermal maximum and critical thermal minimum. And when you look across all of Puerto Rico and Jamaica, what you see is invariably, in every case where morphologically similar species co-occur, they differ in thermal physiology. Okay? So this is evidence that this divergence in thermal physiology is also facilitating the maintenance, as does morphology, facilitating the maintenance of these very diverse communities of anoles in the field. So, question 4. How common is climatic niche divergence across the radiation? So I've been focusing mostly on Puerto Rico and Jamaica. How does this sort of play out across the radiation? For this, I did a good old-fashioned parsimony analysis, where I simply went to the data where all the anoles, the natural history literature, and where all the anoles are categorized by either warm niche, cool niche, or generalist, where they can occur in either niche. And I simply asked across this radiation, how many climatic niche divergence events have we observed? And what we see is that there have been about 30 niche divergence events. Now, I also did this for ecomorph categories, right? How many times has there been a transition in ecomorphology? So let me turn this over to the audience. How many ecomorph transitions do you guys think have occurred? We have 187 species in this phylogeny, 186 divergence events. How many times do you think there's been an ecomorphological divergence?
20.
20, okay. 30, that's a pretty good one. Anyone else?
33.
30? 60. I should really do this by like the Price is Right way. So, you can't be over, but if you're under, it's good. So actually what we see is 25. Okay? So we got some good.
Somebody's really higher,
Yeah. So what we see here is that, you know, the ecomorphology story is sort of what you think about when you think of the anole radiation. But this climatic niche divergence and evolution of thermal physiology may be at least as important, if not more important, for this radiation. And I think this has importance outside of just the Anolis radiation, because the study of adaptive radiation and evolutionary radiations in general is really focused on morphological traits. And there's a lot of good reasons for that. You can track morphology through the fossil record. You can go to a museum and collect a lot of data very quickly on a lot of species. So physiology is not as easy to measure. But we shouldn't just discount it. And in cases, even in classic cases of morphological evolution driving adaptive radiations, physiology could be very important. And I think it'd be nice if that was sort of a little bit more on people's radars when they're thinking about what drives evolutionary radiations. So let's move to the second part of my talk. Evidence for contemporary evolution of thermal physiology within Anolis. It might surprise you to know that despite the data that I just showed you, within the thermal physiology literature and within the herpetological literature, it's actually thought that thermal physiology evolves very slowly within reptiles, and lizards in particular. It's evolutionarily rigid, okay? And even in the anole case, the Anolis adaptive radiation is a lot older than we originally thought, so a lot of those divergence events you saw were many millions of years ago, and we're seeing differences in physiology of 3 to 4 degrees Celsius in optimal temperature and thermal tolerance. So maybe indeed it is the case that thermal physiology does evolve slowly within reptiles. But all of these are based on comparative analyses. And what we really don't have is any evidence, any sort of longitudinal studies to look at how quickly physiology can change when it's not averaged over these very long branch lengths. So Manuel and I decided to try to tackle this by exploiting a recent introduction of Anolis cristatellus from Puerto Rico to Florida. Just so we're all on the same page here, this map is not to scale. Puerto Rico is not a giant landmass between Florida and Cuba. So this, okay, we're good? So they've been introduced to Florida, and what's nice about this is there are a lot of dedicated herpetologists in southern Florida, and as a result of that, we know when these guys got there, and it was about 40 years ago. Not only that, we know from phylogeographic work done by Jason Colby, the specific source location within Puerto Rico for these introduced lizards. They're from this northeastern corner of the island. So we have a situation where we have an introduced population, we know when they arrived, and we know how long, and we know where they came from. What's interesting about Florida relative to Puerto Rico is that Florida gets much colder than Puerto Rico. What you're looking at here are mean maximum and mean minimum daily temperatures for Puerto Rico in red dashed lines and Miami in the blue. And we see that upper temperatures are very similar for Puerto Rico and Miami. But that Miami gets much colder, and by about 10 degrees Celsius on average during winter months. Okay? So what this means is that these lizards that showed up in Miami experienced essentially instant climate change and conditions much outside the range of what they ever experienced in Puerto Rico. This to us, and despite this, they've managed to persist for at least 40 years. This to us seemed like a good situation where you might expect selection to be occurring, where you might see evolution of thermal physiology. So what we did was go to the source population, and we went to the introduced population in Miami. We collected animals and we brought them back to the lab, and we measured their upper and lower thermal tolerances. And I'll just tell you straight away that we saw no difference in upper thermal tolerance, which you wouldn't expect because there are very little differences in upper temperatures between these two sites. But we did see differences in lower thermal tolerance. So what you're looking at here is critical thermal minimum. This is lower thermal tolerance. the lower the value, the more tolerant you are of cold temperatures, so lower numbers are better in this case. We collected lizards in Miami at two different time points, in the spring and the fall. And we collected lizards from Puerto Rico in the fall. And what we see is that lizards in Miami could tolerate significantly colder temperatures than those from the source population in Puerto Rico, by about 3 degrees Celsius. So this is evidence that there has been selection and actually evolution of thermal tolerance within this group. Now, of course, it might be that what we're seeing here is some sort of plastic response, that it's not a fixed difference, but maybe these lizards in Miami were experiencing colder conditions before we actually measured their CT min, and what you're seeing here is some sort of acclimation instead of a fixed response. But we do have evidence, or we do have data on what the thermal conditions they experienced before we measured them are. So what you're looking at here, this is on the x-axis is days before we measured them. So we measured them right here. And this is air temperature at the sites where we collected them. And what we can see, a couple different things. The lizards in Miami during the spring experienced significantly colder temperatures than lizards in Miami during the fall, with this dark blue line here. And yet we saw no significant differences in thermal tolerance between those two groups. More importantly, the lizards that we collected in Miami in the fall experienced very similar thermal conditions to lizards in Puerto Rico for at least 7 weeks before we collected them. And we still get this significant difference in thermal tolerance. So overall, this is very strongly suggesting that what we're looking at here is a fixed difference between the source and introduced population in thermal physiology that's evolved within the last 40 years. Now, of course, this isn't a slam dunk, but it's the best evidence we've seen that thermal physiology in reptiles can evolve quickly, and that maybe we've been grossly overestimating the rigidity of their thermal physiology. And we're actually sort of pursuing this a little bit more. We're doing some molecular physiology, where we've challenged lizards from both of these populations with different thermal conditions. We're doing molecular analyses to maybe look at mechanistically what might be going on or what might have changed between these two different groups. Okay, let's switch gears a little bit and talk about climate change. Analysis of climate change vulnerability that I did with Anolis cristatellus. And I'll start this part of my talk off by relating the results of a recent meta-analysis in global change biology. What this meta-analysis found was that, on average, biologists use climatic data that are collected at spatial scales 10,000 times larger than the animals under study. So we're often thinking about thermal environments at a very large scale for very small organisms. And to put this 10,000x number into some perspective, if you were to imagine that this entire screen was a patch of habitat, the animal in it would be smaller than this dot that I've drawn on the screen right here. Okay? So what are the consequences of thinking about climate at such a large scale? Well, this is an aerial view of a patch of forest that was one of my sites in Puerto Rico. If you look very closely, you can see there's an Anolis cristatellus on this tree right here. And I think, so I should say that, in these broader scale climatic analyses, this is equivalent to 1 square kilometer. And this whole patch of forest would be considered thermally homogeneous, I should say, in these broad scale analyses, okay? And I think just from looking at it, you can see that a lizard within this habitat is not going to experience this as a thermally homogeneous piece of forest, right? We have areas that are very open. We have areas that are heavily shaded. There are different slopes and aspects which are going to influence how much insulation they receive. There are patches of ground that are exposed rock and patches of ground that are covered in leaf litter, which is going to influence how much radiation is coming off of the ground. All of these things add up to making this actually a very complex thermal environment for a lizard within it. So global climate change is happening at a global scale, but the consequences of it for organisms are happening at their scale, at a very small scale, right? So what I was interested in is doing a very fine scale analysis at the scale of the organism with cristatellus. So how did I do this? Cristatellus in Puerto Rico occurs in two very distinct habitat types: mesic forest, sort of wet tropical mesic forest, and dry xeric forest. There's one swath of xeric forest down here in the southwest and another patch up here in the southeast where that source population for the previous study was. What I did was go to 9 sites across Puerto Rico, 4 mesic and 5 xeric, and I measured 3 different things. First, I measured their body temperatures. I measured about 1,300 different lizard temperatures across these 9 sites, the old-fashioned way. I also measured their operative temperatures, so using those models that I talked about previously. And then I took lizards back to the lab and I measured their thermal physiology. And then I integrated all these together to estimate what are the physiological conditions, sort of what's their physiological performance now within these habitats, and then to project ahead to what their physiological consequences of climate warming will be. And just to give you an idea of how different these habitats are, this is mesic habitat on the left, relatively high canopy, moist forest, relatively shaded understory. This is the xeric habitat on the left, which is sort of a desert scrubland, very low, shrubby canopy, considerably more open than the mesic habitat. Now interestingly, it's been hypothesized that in the tropics, populations living in closed canopy forests might be more vulnerable to warming than those in more open canopy forests, because there's less thermal variability, less spatial thermal variability within shaded forests. What that means is that animals in shaded forests won't be able to employ behavioral thermoregulation to buffer themselves from temperature change, which you can get in a more open habitat, okay? So here we have a species that occurs in both of these habitat types, and we can look at this hypothesis within this single species. So I'll go to the data. I'll start with the physiology. What you're looking at here is the thermal performance curve again. First thing to note is that there was no physiological divergence between the animals in the xeric habitat in red and the mesic habitat in blue. Now, where do their body temperatures fall relative to this performance curve? So here's just a summary of the body temperatures that I measured. It's kind of depressing to take 1,300 lizard body temperatures and make two small bars like this. But basically what we have here is what we see is that lizards in the xeric habitat are experiencing significantly warmer body temperatures than lizards from the mesic habitat by about 3 degrees Celsius on average. And one thing to note, though, is that this range of body temperatures for both of these populations keeps them at relatively high, a range of temperatures that keeps them at relatively high physiological performance, okay? Now, in Puerto Rico, by the end of the century, we're expecting air temperature increases of about 3 degrees Celsius. And with that information, we can project ahead to how these body temperature distributions will shift. And here's what we're expecting. So in the mesic habitat and xeric habitat, body temperatures will both increase. In the mesic habitat, we can already see evidence here that it looks like it's going to be worse for the xeric habitat lizards than the mesic habitat lizards. This shift is going to keep mesic habitat lizards still maintaining within a relatively high physiological performance range, whereas these xeric habitat lizards, it looks like they're going to be sort of pushed off this physiological cliff, right, and experiencing very low physiological performance under warming. But remember, these xeric lizards are living in potentially a more thermally variable habitat, and maybe they can use behavioral thermoregulation to buffer themselves and avoid these really high temperatures. And we can address that with the operative temperature data that I collected. I'll start by showing you the operative data from the mesic habitat. So this is time of day on the x-axis, body temperature or operative temperature on the y-axis. What we can see is that within this representative mesic habitat, throughout the course of the day, there's relatively little thermal variability at any given time. So there's little variability for these animals to exploit for behavioral thermoregulation. And indeed, when you look at their body temperatures, the operative distribution and the body temperature distribution are essentially right on top of each other. This is what we call thermal conforming, right? These lizards are thermal conformers. And so as operative temperatures rise, their body temperatures are going to be pulled along with it. But there's not going to be a big physiological consequence of that, probably. In the xeric habitat, as expected, there's a lot more thermal variability at any given time. What this means is that as these operative temperature distributions shift upwards, maybe the lizards in the xeric habitat are going to be able to start favoring these cooler microhabitats and buffer themselves from those increases in temperature. But when we look at what their body temperatures are now, what we see is that they're already behaviorally thermoregulating, and they're already favoring and sort of hugging the lower bound of the temperatures that are available. Okay? What this means is that as these operative temperatures increase, their body temperatures are going to be pulled along with it. And they're going to have very little opportunity to behaviorally thermoregulate to buffer themselves from warming. So putting this all together, we can look at what the physiological consequences of warming may be in Anolis cristatellus across these different sites. And here's what you find. What you're looking at here is the predicted change in physiological performance for lizards in each of the mesic and xeric sites. And we find that in the mesic habitat, there's going to be very little physiological consequence of the warming that they experience, and actually potentially a slight increase in physiological performance. Whereas in this more open xeric habitat, we're expecting significant physiological consequences and decreases in physiological performance by 25 to 30% on average. So by taking this very fine scale approach, we're able to see that, you know, the expectation of open habitat species being able to exploit behavioral thermoregulation to buffer themselves might not actually be true and might not hold up. And I think analyses like this are becoming more common, and hopefully we'll get more of them and eventually be able to build, you know, with a fine scale analysis like this, it's hard to think beyond the organism that you're actually studying. You know, it's a very specific analysis, but hopefully as we build more and more of these analyses, generalizations will start to emerge about the types of operative thermal environments and the types of organisms within them that are going to be particularly vulnerable to warming. Okay, so now we'll move away from my dissertation work and talk about some of what I've been doing in Jonathan's lab. And this is looking at the evolution of thermal plasticity across ectotherms. So, given the reality of climate change, there's been a sort of resurgence of interest in understanding plasticity in thermal physiology and looking at broad patterns of plasticity. And the reason, of course, is that plasticity allows you to adjust to changes in your conditions, right? Plasticity is the ability of a given genotype to exhibit different phenotypes under different environmental conditions. So you might expect that a species or population that can inherently change along with thermal conditions without needing to undergo evolutionary change might be less vulnerable to warming than a population that doesn't have that capacity, right? So there's a lot of interest in these broad patterns of plasticity. And there are two general hypotheses that have been put out there to explain variation in thermal plasticity across ectotherms. The first is what I'm going to call the variability hypothesis. And this one is very straightforward and intuitive. It says organisms that occur in more variable thermal environments should have greater plasticity, should favor the evolution of thermal plasticity and the maintenance of plasticity. And there's a geographic manifestation of this hypothesis, which is that you expect a latitudinal climb in plasticity. Because as we know, organisms in the tropics experience much less thermal variability than organisms that occur at high latitudes, right? So what you expect, and what many people expect, is that you'll see a positive relationship between plasticity and latitude, okay? And with respect to climate change, this expected pattern has been used to argue that tropical organisms may be particularly vulnerable to warming, right? Because they shouldn't have a high capacity for plasticity, they should be particularly affected by warming that occurs. The second hypothesis is what I'm going to call the trade-off hypothesis. And this isn't built so much on sort of theoretical considerations, but empirical observations of groups occurring in different thermal environments. And it was sort of, so the general idea of this hypothesis is that organisms that have adapted to more extreme thermal environments have less capacity for plasticity and thermal tolerance, okay? So Jonathan was one of the first to sort of spearhead the idea of this hypothesis. And here's some of his data from, excuse me, porcelain crabs. I'll take a minute to go through this because it's not necessarily straightforward at first. So on the y-axis here, we have basically acclimation capacity, okay? Your ability to acclimate or your plasticity capacity. Each one of these dots is for a different species of porcelain crab. And I'll start with the open dots, which represent plasticity in the critical thermal maximum or upper thermal tolerance. What he observed was that species that were adapted to warmer conditions had lower plasticity and thermal tolerance, okay? So the warmer the conditions you're adapted to, the less plasticity you have in thermal tolerance. This also works for critical thermal minimum. The colder the conditions that you're adapted to, that's indicated by these black dots here, the colder the conditions that you're adapted to, the less plasticity you have and lower thermal tolerance, okay? This actually leads to a somewhat unintuitive result with respect to climate change, which is that organisms that are adapted to warmer conditions may be particularly vulnerable. Even though they have tolerance for high temperatures, increases in temperatures may affect them, may be particularly bad for them because they don't have the ability to have these plastic responses, okay? So both of these hypotheses have been tested at sort of a narrow phylogenetic scale, looking across a few species of Drosophila or some porcelain crabs and things like that. And so far, the results have been equivocal. What we really haven't had is a comprehensive analysis, really across ectotherms, to look at whether these patterns are occurring generally. And that's what I'm trying to do, and that's what I've been working on in Jonathan's lab, one of the projects. So what I've been doing is compiling data on plasticity from the literature. And just to talk about a little bit what I mean by when I say thermal plasticity, if we have critical thermal maximum here on the y-axis and acclimation temperature on the x-axis, what we see in general is a pattern that thermal tolerance increases as the thermal conditions an organism experience increases, okay? And you see the same general pattern with critical thermal minimum. So I've been compiling data from the literature. I have estimates of critical thermal maximum plasticity for about 280 ectotherm populations and plasticity and critical thermal minimum for about 114 populations. And these data are across 5 major ectotherm clades. We have insects, crustaceans, fish, amphibians, and reptiles. So we have invertebrates and vertebrates represented, and aquatic and terrestrial organisms represented as well. And my metric of plasticity is what we call the acclimation response ratio. This is essentially just the change in slope, or this is the slope, I should say, of the relationship between thermal tolerance and acclimation temperature. So it's essentially the slope of the line through these data. The greater the slope, the greater the plasticity. Okay? And I tested these hypotheses using a linear mixed modeling approach. And to account for the non-independence among data points, unfortunately, I don't have a tree that covers all 5 of these major ectotherm lineages. So in lieu of that, what I have is in each one of my models, random hierarchically structured taxonomic term that does some accounting for non-independence based on taxonomy. Okay? It's not ideal, but it's the best I could do given the situation. Well, let's get right to the data. I'll start with the expectation that plasticity or capacity for plasticity should increase with latitude. And we see no evidence for that whatsoever. So you're looking at plasticity and critical thermal maximum here, and absolute latitude on the x-axis. So I'm using absolute here because I included hemisphere and interactions with hemisphere in all of my models, but it never came out as significant, so we just have the absolute latitude. And what we see is, no evidence of a positive slope whatsoever with latitude and plasticity. What we do see, what does come out as significant, is a habitat effect, where organisms in aquatic habitats, freshwater and marine, have higher plasticity than organisms from terrestrial habitats. And we can break this down by clades, so you can look for your favorite group of organisms on here. And you can see that basically in every case, there's no evidence of this positive relationship between plasticity and absolute latitude. So what about for critical thermal minimum? Same story. No evidence of increased plasticity with latitude in critical thermal minimum. Same general pattern shows up though, where organisms from aquatic habitats, freshwater and marine, on average have higher plasticity than those from terrestrial habitats. We can again break this down by the different clades. Very little evidence. There's only one group where there's possibly evidence of an increase of latitude, and that's in reptiles. So across critical thermal maximum, critical thermal minimum, all these clades, very little evidence that there's an increase in plasticity with latitude as one would expect. So what about this trade-off hypothesis? Well, it turns out there's no evidence for that either. What you're looking at here is, again, critical thermal maximum acclimation response ratio. The x-axis is the maximum critical thermal maximum for each of these species. So this is the warmest temperature that the organism could tolerate. We see no relationship. We would expect a negative relationship with this trade-off if CT max was trading off with plasticity and capacity. And we see the same thing with critical thermal minimum. Here we would expect a positive relationship, no evidence of a relationship at all. So what if we break down these plasticity data just generally by clade? So here we have, I'll start with CT max plasticity again, CT max acclimation response ratio by these 5 major clades. what we see is what we'd sort of expect based on the habitat analysis, where crustaceans and fish, which are primarily in aquatic habitats, have higher acclimation capacity than amphibians and insects and reptiles that are occurring primarily in terrestrial habitats. Something else I'd like to point out, looking at the data like this, so this 0 would be no plasticity at all, and this 1 would be perfect compensation if tolerance perfectly tracked the change in thermal environment, right? We can see that basically all ectotherms are really bad at plasticity. None of them are anywhere near perfect compensation with changing conditions. And this is important because one of the things we're expecting with climate change is not just increases in mean temperatures, but increases in extremes and heat waves and extreme thermal events. And what this is saying is that even in organisms that, relatively speaking, have high plasticity, if this is their thermal tolerance and this is their body temperature, and we have this gap between them that is sort of their buffer from overheating, right? As their body temperature is warm, they're going to be able to increase their tolerance, but not as much as the temperature is increasing. So even in species that have relatively high plasticity, as the climate warms, their buffer is going to get much, much smaller. Okay? But it's going to be particularly bad probably for terrestrial organisms. And we see this general pattern we see also with critical thermal minimum. So all of this together, I think, leads to the question of, well, first, it suggests that the primary hypotheses that we have out there for what drives broad patterns of plasticity in thermal physiology and ectotherms don't really explain much, right? They don't have a lot of explanatory power, which means we need to come up with maybe other hypotheses that are driving these patterns. As for what those hypotheses are, I currently have no idea. I was really expecting, once this analysis was done, that I'd be talking about the relative strengths of these patterns instead of no pattern at all, right? And this is a relatively recent analysis. I just finished this in August. So I have some general ideas for maybe what might be going on, but they're certainly not bulletproof right now. And instead of BSing through those, I'll just leave it at that. And if you have ideas, I'd love to talk to you about them afterwards, to come up with maybe ideas for what might be driving these general patterns. But there are consequences that we can talk about, despite the fact that we don't necessarily have a mechanism. So we already have this idea that all ectotherms are bad at plasticity, and that's going to be bad for climate change. But what these data also suggest is that the expectation that tropical lizards will be tropical ectotherms will be particularly bad off, will do particularly poorly under climate change, doesn't necessarily hold water. Animals in the tropics have just as much plasticity capacity as those at high latitudes. So for that reason, they're not going to be inherently more vulnerable to warming. Another interesting thing about this is that aquatic habitats are probably not going to change as much as terrestrial habitats with respect to temperature. Because of the high heat capacity of water, you just don't get as much change in temperature. But what we find is that aquatic organisms have the greatest ability to respond to changes in thermal conditions. So it might be that aquatic organisms are going to be maybe I should say terrestrial organisms are going to be particularly vulnerable relative to those in aquatic habitats. Okay. So I'll just end with one other thing that I'm contributing to in Jonathan's lab, and that's looking at the molecular mechanisms of plasticity and thermal physiology. So I'm sort of trained as an organismal physiologist and as an ecologist. I'm trying to sort of build up my molecular toolkit so I can be able to address these questions at sort of multiple levels of biological organization. And to get my feet wet with that, I'm contributing to a project that Jonathan's doing in collaboration with Mary Power that was spearheaded by a previous postdoc here, Scott Fay. And what we're doing is looking at transcriptomic responses of 4 species of aquatic insect larvae that occur in streams in California, to look at how they respond to changes in temperature, to come up with predictions of maybe how these communities might be changing under changing thermal conditions, and what the ecological consequences sort of upstream of that will be. So that's another project that I'm working on in Jonathan's lab. With that, oh wait, I do have one other slide. I've talked about a lot. So what have we learned? Quick review here. Well, First, we've learned that morphological divergence does not a whole adaptive radiation make, right? Physiological divergence can be really important for radiations, and in particular for the Anolis adaptive radiation. Second, thermal physiology can potentially evolve very quickly, even in the lowly reptile. Third, scale matters. We're all thinking about mechanistic analyses of climate change and predicting vulnerability of organisms to that change. Third, is that fourth? I can count, I swear. We have a lot to learn about what drives variation in plasticity and ectotherms, because the hypotheses that we have right now do not have a lot of explanatory power. And last, I don't know a lot about molecular physiology, but I'm learning. And with that, I'll take any questions.
Species, because, or just any montane species, if you think about it, if you're in a tropical mountain, your diurnal temperature range can be really large. It can be really cold around midnight. It can be super hot at noon, and so you don't have a big annual range. Every day to day might not be that different, but during a single day, you have an enormous temperature change.
So I did not include altitude in my analyses. It's something I can do. I do have the altitudes for all the measurements that I did. In general, though, the pattern of variation in thermal conditions that you experience with altitude are not as strong as variation in the absolute conditions that they experience, right? Because a lot of the latitudinal variation that you see in temperature is driven by changes in insolation throughout the course of the year, which you don't get with altitude in the tropics. But it is something I could incorporate into the analyses. It's not going to influence the marine organisms and most of the freshwater species because they're all low elevation.
Yeah. But the other ones.
Yeah, it could influence them.
Yeah, for the meta-analysis part, I thought maybe you can divide it by scale or microhabitat. So like for example, like fish, maybe you can do freshwater ocean, and one might
Well, I did
is
that.
more
That was
plasticity,
actually
yeah.
incorporated into the analysis.
Like
So
or like
the
reptile,
habitat-
yeah, for like desert living reptiles versus or whatever. You can maybe separate the not reptiles and fit into a more wider.
Yeah, it could be that
something like
it could be that partitioning it at a finer scale
Yeah.
would actually lead to more resolution. I mean, I have to say though, given the amount of data that I have there, it's very surprising. I think that no pattern emerges at all. Like it's not even a suggestion of a pattern. It's completely flat. So that might explain it, but I would be surprised if that would actually explain what I'm seeing. Yeah.
So Barry Sinervo has been discussing a lot of these ideas also from his work in Mexico and the Mexican colleagues.
Yeah.
How do you connect your work to that? What do you conclude?
So actually at my Herb group talk, I talked a little bit, so I actually did analyses of changes in activity patterns with temperature within these anoles and how that would influence their vulnerability to warming as well. I didn't talk about it here, of course. So doing similar things to what Barry has done. And from that analysis, the link is, I don't think Barry has the correct mechanism. I think he's overestimating the constraint that temperature has on activity. So I'm not sure about the patterns that he's finding that emerge from those analyses. So that would be my response to that. Maybe sometime we can talk about the data that I have and compare it to Barry's. Mike.
So it seems striking that the ocean environment and the aquatic environment in general is less variable in temperature than the terrestrial environment, and yet terrestrial organisms are less physiologically plastic.
Yeah.
Do you have any, one of the confounds there obviously is that you're talking about different groups of organisms in those cases, but like even say like within insects, even perhaps within insects that shift within their life cycle, do like dragonfly nymphs show different physiological tolerances than dragonfly adults or things like that? I'm just curious if it's like a general pattern or what's going on.
Yeah. So what I did was some of the insect data and some of the amphibian data were collected on aquatic morphs, right? So I looked at whether you get the same general pattern comparing the the primarily aquatic to these other groups. Let me just show you those data. I have a whole bunch of analyses I didn't show you. So this is critical thermal maximum acclimation response ratio. for insects and amphibians that were measured in water, compared to the fish and crustaceans that were all measured in water. And we see the same general pattern. So it might not actually be habitat per se that's driving these differences. It is the fact that organisms that are predominantly aquatic have greater plasticity, but it doesn't look like it's something about living in water per se that necessarily is driving these patterns, because these primarily, what we think of as terrestrial organisms, the pattern of low plasticity is maintained even when you measure them in water. Jim?
I was just wondering if behavioral thermoregulation has anything to do with this. Like if you're living in the water and there's all this thermal inertia, the organism has to be physiologically plastic or at least tolerant in order to deal with the temperature, whereas if you're outside of the water and you can thermoregulate, maybe that's another way of avoiding a temperature that wouldn't otherwise be.
Absolutely, and that's one of the mechanisms I've been thinking about that may be leading to this difference between aquatic and terrestrial organisms. It's absolutely true that you just don't have the availability of behavioral thermoregulation in aquatic habitats as you do in terrestrial habitats. What sort of throws a wrench in that is that when you look at body temperature data for, even if you look like within fresh water, the range of temperatures that tropical freshwater species experience relative to high latitude species, there's still a huge difference in the range of temperatures they experience. The high latitude species experience way more variation than the tropical species, and yet you still see that there's no latitudinal gradient within that habitat. So maybe behavioral thermoregulation and the lack of it is one thing that's contributing to it, but it certainly couldn't be, I don't think it can be the whole story. Yeah.
You paint a fairly optimistic picture of the aquatic environment, but of course climate change involves more than temperature change.
Sure.
So the things like pH and so on in the water could be much more important.
Absolutely.
As well.
Absolutely, yeah. What these analyses are not incorporating, particularly in aquatic environments, are the sort of multiple stressors that can be changing at the same time. Actually, one thing we're working on in Jonathan's lab right now is a project looking at sort of how multiple stressors, how the timing of multiple stress events is changing or currently occurs, and how we expect it to change in the future, and how we expect that to influence the physiological responses of organisms. So it's something we are considering, but doesn't, especially in terrestrial habitats, it's not as important, but absolutely in aquatic habitats, yeah.
Maybe one more.
Can I ask another?
Yeah.
So this is actually about your initial section where you were talking about the evolution of the thermal divergence. Yeah. That was surprising to me that you could have two trunk ground anoles living together in sympatry that have different thermal preferences. How is this actually manifest? Like, is one of them a thermoregulator and another a thermoconformer? I mean, they're living in the same general condition.
Yeah, it happens on the scale of meters, right? So the thermal conditions that you experience, so if you're standing, we all experience this, if you're sitting in the shade and then you go out in the sun, you're experiencing very different thermal conditions. And that's basically the scale at which they're partitioning these thermal environments. When you see both types of species together, it's usually at an edge, right, of a forest and a more open habitat. And sometimes it's a little more fine scale than that, but basically the warm niche species is sitting in a sun spot and the cool niche species is sitting in the shade. I mean, it is
Same
really
tree.
surprising.
Same tree.
Yeah, sometimes you actually do see them on the same tree. And it is surprising that you see this physiological divergence. These are all in the tropics too, right? And they're occurring in the same place, and we don't think of the tropics as having a lot of thermal variability. But somehow they are partitioning at this extremely fine scale. It's very interesting that works. Yeah.
There's one other question, maybe?
Yeah.
Yeah. Do you see any difference in body size between the warm and cool niche species?
There is not a consistent difference in body size. In some cases, one is bigger than the other, but not in all cases.
Okay, so not a discernible pattern across the board.
Not a discernible pattern.
All right. Thank you very much, Alex.